We have a pipe properties module, a chemical resistance guide module, flow analysis, water hammer, span and thermal analysis, followed up by buried pipe energy loss module. So let's start with connecting, registering. First, you have to create a MyNOV account. To do this, you register at this address right here, https:// caps.nov.com. It will take you to this landing page that you see below. If you're registering for the first time, you have to click on the MyNOV registration button. If this is your registration first time, please click on the word here in red letters, and you will get a PDF with detailed instructions on how to navigate the registration system. Okay, let me go to the software and demonstrate how to log on once you're registered. Again, it's the same address, https. I've been here a few times, so it comes up automatically. Here we are. I need to log in. If you're a non-NOV employee, you will go to My NOV and register. Since I'm an employee, I click on My NOV employee button. I type in my registration email address and my password and sign in. After a few moments, you'll land on what's called CAPS Connect, and it says that I have 2 approved applications. So click on that, and you'll see 2 here. Where we want to go is to Success Design. So let's launch the application. Okay, the software starts up in the Piping Products module. Gives you a few hints on how to get started, what to do to get, to enter data. Essentially says, select a product market by clicking on Chemical Industrial display to display all of our different markets. We have oil and gas, marine and offshore, fuel handling, C&I markets plus mining, and they're all under this drop down here. If I click on Chemical and Industrial, it'll give me the drop down. I'm going to stay in Chemical Industrial because that's where the majority of our viewers are right now, I believe. So the next step is to select the product classes. You can just simply say all products, and you'll get a tremendous number to choose from. Or if you want to narrow it down to something like our Centricast products or our Bondstrand products, you can click on them. Let's select Centricast. Now, under the Centricast, there are several products as well. There's the CL1520, 2030, 2530, and Z-Core. I'll click on Z-Core. Software reaches out to the database and says what diameters are available. 1 inch through 14 inch. Let's go ahead and select 14 inch. Now, what can we see in this module? Under the Properties subtitle here, you'll see several radial buttons, they're called. One for dimensional data is already selected, and that's what we're getting on the right side over here. You see the diameter, the inner diameter, outer diameter dimensions, 3.94 inches, or in the SI or metric system, it's 100.1 millimeter. Down here we have it broken down into the wall thicknesses of the pipe, the total wall, the reinforced wall, and the liner thickness. Down here we have the weights of the pipe in pounds per foot or newtons per meter, or some use mass, it would be like kilograms per meter. And then finally, we have the engineering cross-sectional properties here. Reinforced area, the reinforced moment of inertia for doing many span calculations, and the flow area and fluid capacity in several different units for you. Okay, let's move on to the next one, which would be material properties. Once this comes up, you'll see on the right-hand side that you have the axial tensile properties per a test called ASTM-D21. The results of that test have been compiled and they're displayed here. You have your tensile elastic modulus in both US customary and SI units. You have the ultimate axial tensile stress for the product as well, 28,000 or 193 megapascals. And we have other subgroups. We have the Poisson's ratios, which there are two with respect to the axial direction of composite pipe. We have apparent beam bending modulus. Then we have our tensile hoop properties. Again, we have another hoop modulus elasticity. And we have the ultimate strengths, which are 30,000. We have some special footnotes here, which will show up. This is essentially saying the software only found one data point at and it was 30,000 pounds per square inch. And it was at 75 degrees. So technically our database only has data ambient temperature 75 degrees. And you'll see why that's important here in a second. Followed up by the shear modulus and the thermal properties such as conductivity and coefficient of expansion. And down at the bottom here are the long-term hydrostatic testing for ASTM D29 test results. These are static test results. The first, you see the number of regression curves we have for this product. Recall, when I say this product, we're talking about Z-Core. The lowest curve was tested at 75 degrees and the highest was tested at 200 degrees. And then we go and say the following data is evaluated at 75 degrees, right on one of the test points. And you see we have the 20-year design stresses and the 50-year design stresses here for you. LTHS just simply means the average stress, mean stress. LCLs represent the lower confidence levels. Typically, this pipe, being Z-Core, is designed according to ASME 31.3. They typically use a 50-year design life and a mean stress, or 16,100 pounds per square inch value. And don't overlook the footnotes down here that reference some of the things like Poisson's ratios. Now, when we clicked on material properties, we got another subtitle here called temperature. Obviously, it allows us to get, it may not be obvious, but it does allow us to get material properties at different temperatures. And if I could recall, these values actually slightly dropped. All the modulus will drop as temperature increases for composite pipe. And down here, you'll see that it tells you that the D2992, the following data, is evaluated at 150, halfway between 75 and 200. It's actually not halfway, but it's interpolated between there. And these are the results. Let's go on to the next button, pressure ratings. And what I'm going to do when I click this button is I'll get the pressure rating for this 4-inch diameter pipe. You see from the screen here that the internal static pressure rating is 150 degrees at 275 degrees. You could interpret that to say 150 psi up to 275 degrees if you like. And of course, that's equivalent to 1 megapascal. Now I do have a footnote here. You see it's right here in the notice here. It says, this is for the pipe, essentially. You need to see the Fiberglass Systems product data and fittings catalog for special fitting ratings. There are often reduced ratings for fittings, laterals for example, or maybe saddle outlets. Large saddle outlets would typically be derated, so you may not carry 150. But for all the primary fittings, 90s, 45s, and Ts, the CentraCast 4-inch will be rated to 150. But don't overlook the notes. Next radial button is parallel plate data. And again, as I drop down this, some of this is specific to the diameter I've chosen here. What I get when I click parallel plate data, I get the results from a test called ASTM D2412, which we call parallel plate. And it was evaluated at 3% deflection of the pipe body. Okay. The hoop modulus is 5 million. The pipe stiffness value and stiffness factor values are right here. Okay. This is diameter dependent. Let me go ahead and switch diameters and show you the difference. You can really think of the pipe stiffness here as a spring rate. And, you know, a larger pipe is going to be, assuming the diameter, the thickness ratio is the same. The larger the pipe stiffness should drop. And it did right here. The modulus is roughly the same for pipe diameters of the same construction. Let's go to the last radio button here. And this one ties back to the material properties. I'm going to go here one more time. It ties back to this ASTM D2992 test data, and it keys off the 20-year LCL, which is the most common value that's used in most piping specifications for fiberglass pipe. So let's go ahead and click on a 20-year design envelope. I realize I'm still setting on the temperature of 150. I could vary that if I wish. And what do I get? I get standard laboratory temperatures, or 75 degree test data for the EA is the axial, EH would be the hoop, and the shear modulus. These are all values you've seen before under material properties. And we also have the elastic properties, again, same ones, repeated at 150. Why have I repeated these twice? Because if you're doing a flexibility analysis with a software program like C2, they're always going to ask you for baseline stiffness or baseline modulus data. And that's what you're looking at right here. Ambient temperature is considered the baseline. And then they would use these values as your design temperature values. One specific program, Caesar 2, which has input specifically geared for ISO 14692, uses this unusual nomenclature. Sigma AS 2:1, etc., right here. So we got S's are short term, L stands for long term, and all the A's stand for axial stresses. Okay. So let me go down and show you how this relates to this design envelope down here. Let me move our ISO design factor. The default for sustained load cases is 0.67. That's why it comes up. But let me drop back to 1. And you'll see that this top point right here is 8769.6. Corresponds to this value right here, 8770, rounded off. And this point here, 9306 and 4698 is going to correspond to this value right here. Okay. And if you notice the other value, 9396 is actually a multiple of the 4698. So it's a multiple of 2. Because, as this may refer up here, this 2:1, it refers to a 2:1 stress ratio of a hoop with respect to the axial direction. What does all this mean? This means if you design a piping system and you keep the stresses of any element in your system below this line or to the left of this vertical line, essentially in the trapezoid, you have a safe design for 20 years at a given temperature. This was given at 150 degrees. It's very simple to change that for a different temperature. Now all these values have slightly changed. Suppose you wanted the design stress and you wanted to incorporate a design factor. ASME, for instance, has a design factor for sustained loads of 2, where the inverse of 2 is 0.5, 1/2. So I could come over here and find 1/2. Oops. I slipped with my left finger there. Okay, and I have new values. Now notice these are much smaller than they were before. As a matter of fact, it could have been 70 to 75, but since I applied a design factor on it, this is the design envelope for the sustained case, you could say. Okay. And what's so nice about the software, suppose you were considering other products, suppose you were considering Green Thread HP series, that you didn't need a premium chemical resistance of Z-Core. You may want to just use a filament wound product such as Green Thread HP16. Notice we have several pressure classes here. And let's go back to the 4-inch. Not that 4 inches magic, it's just size I enjoy using. And you see we're getting exactly the same data over here, but the design envelopes are different. This is a filament wound product, whereas the Z-Core product is a centrifugally cast product. And the reason the shape of the curve is different is because the filament wound is made from winding glass fibers on a resin at a plus or minus 55 degree reciprocally wound angle. And the cast pipe essentially is built up of 0 and 90 degree reinforcement embedded in resin. It's the beauty of composites. You can tailor them to what you need. It's a subject for another webinar, actually. But last but not least, we have these documents right here. And what these documents right here are links to our website. For instance, if you are interested in the piping data for the product selected here, Green Thread HP16, you could click on this link. Let's open it. So you've got essentially the printed literature here if you'd like. Now I can save this to my computer, I can read it, I can discard it, whatever I'd like to do. Okay. Got too many things open here. And here I have a link to our installation manual for the GreenThread product as well. Very handy, very, very handy indeed. Okay. So that pretty much sums up all I can think of to tell you right now about the pipe properties module. It gives you dimensional data, material properties, and that all-important design data for the mechanical engineers or civil engineers doing the pipe stress analysis. The next module I want to go on to is the flow analysis. I'm going to skip WaterHammer for now because it's essentially a subset of the flow analysis. Okay, we start basically the same way. It's carried forward the GreenThread HP system and HP16 system we were using before. When you go from module to module, you do lose your pipe size. It defaults to the smallest size. So let's go back to the familiar 4-inch diameter one. Okay. Now, suppose you wanted to do a flow analysis on corroding steel pipe, for instance. You could click on Custom Product here, type in a description, because if you do any printout, this is what will be on your output. Okay. Having a little fun here. And then you just input the pipe size, the inner diameter, the roughness of the inside of the steel pipe, or whatever product you may be wanting to put in here, and the pressure rating. You may leave the pressure rating out because steel pipe really doesn't have ratings, but you can rough one out if you'd like. It's this pipe roughness that is so important. And we'll talk about that a little bit later when we look at the output here of this module. So let's close this because I don't want to run any corroding steel pipe. The next thing we'll select, this is all input on the left, by the way, is the type of fluid running through it. And again, we have a drop down with several different compounds in it. And we've got acetic acid, crude oil, gasoline, diesel, jet fuels, methanol. Let's just select water at 60 degrees. Seems to be a reference. And we're all familiar with it. Suppose you did not want to do an analysis on water, but sulfuric acid, and you didn't see it in the list. Again, you can create a custom product here. In this case, it's a fluid. And what you need there to do the analysis is the specific gravity, SG, and the viscosity in centipoise, and some kind of description here of the fluid itself. It might be, what did I say, sulfuric acid, for instance. But I don't want to set anything here, so I'm going to close. These custom buttons give you a lot of flexibility, though, with the software right here. Now, more input is the pipeline length. Suppose your length was not 100, but 1,000 foot long. Now, I'm not going to mess with the flow entry at the minute, but the default is velocity. There's several types. We could do it in gallons per minute, liters per minute, cubic feet per minute, barrels per day, etc., etc. Let's leave it with feet per second. The default comes up at 5 feet per second. Why does it start at 5? Because that's usually a very sweet spot for flow calculations. It's usually where you see high efficiency and low pressure losses. That's really what you want in a pipe system. Low pressure losses and high efficiency, which cost you the least amount of money to operate. So now we have all of our input. Let's see what the software has told us about the GreenThread HP16 piping system and water. It says, well, you've selected 4-inch pipe. That pipe diameter is rated 300 psi. And as before, this is the pipe rating. Check your fittings. The pipe size is 4 inches in diameter. And here's some more geometry. ID, the viscosity of water, the specific gravity of water in 1. And this is really what we're looking for. What's the pressure loss of this type of flow through 1,000 feet of 4-inch GreenThread pipe? It would be 8 psi, right on the money. I didn't select that. That's a coincidence. So we are going to lose 8 psi for every 1,000 feet. So if you had a 10,000 foot line, you could just multiply that by 10 to see 80 psi drop there. Okay. And Civil engineers sometimes don't like to talk PSI. They like to talk head loss in terms of feet. Now, this would be feet of water in this case. 18.5 feet would be the head loss in this system. This is a Reynolds number. Kind of shows you that you're in the turbulent zone. Actually, anytime you're in the sweet spot over here, 3 to 7.5 feet per second, you're going to be in the turbulent zone. The pipe roughness, which is in the database, for fiberglass, all of our fiberglass pipe will be the same number, 0.0000175, and that's in feet. Or here's the metric equivalent. Okay, so we got the pressure loss through the pipe body itself. What if we have fittings in that system? If we have fittings in that system, let's look at the fitting head loss section. Makes sense. What do we got? Quantity of fittings, fitting types, and then the output would be the head loss in feet, similar to what we had up here, or the pressure loss in PSI. I haven't duplicated this in the metric system, but it's quite convertible. So let's consider long radius 90s. Suppose we had 25 of those in the system. You're seeing we're going to lose like approximately 1 PSI for those 25 fittings. Not too bad. Let's look at some 45s. Let's say we've got a dozen of them. 12.232. Not much at all. So let's look at what we've got so far. We've got a pipeline that's running horizontal with about 37 different types of fittings in it. 37 fittings of 2 types, I should say. The theoretical horsepower assumes some pumping efficiency. 0.9 is the default. You can make it whatever you like. It could be 0.8 sometimes. That's a realistic number too. But the horsepower based on the pump efficiency like required would be 1.34 horsepower. Okay, maybe you're interested in how much electricity you're going to be using to run this. It's like the equivalent of 1 kilowatt. Okay, 1 kilowatt per hour. So it's going to cost you what? 1 kilowatt costs about 15 cents an hour. Not too bad. Okay, let's go back and look at this system. It feels like something may be missing. Yes, here's another input right here. There's a big box. Notice the inputs down here are all highlighted in boxes, so you know that's looking for data from you. It's the same over here. See, we got all the input boxes here. So let's say we have an elevation change. Suppose this system rises, let's just say 35, 350 feet is a lot. Let's go to 35 feet. Okay. Now we see that our losses, just for that 35-foot elevation change, which is a head loss, in terms of pressure is 15 psi, just to overcome the elevation change itself. So we have a total head loss for the entire system being the pipe and all these fittings selected, of 56 feet or 24 psi. We can go over here and go, now because of this 35 feet head loss, we're required to use at least a minimum of 3.54 horsepower pump, which burns 2.64 kilowatts. Remember, it was exactly 1.0 a while ago. So now because of that elevation change, we're burning 260% more electricity. Still relatively inexpensive, but it shows the functionality of the module right here. Okay. It's, like I said, it's easy to switch to GPMs. Select the right button, type in, say, 225 gallons per minute, which is approximately 5 feet per second. And you see we roughly got the same answer over here. Apparently 5 feet per second is like 224, 222. So it's that easy to change. If we wanted to, suppose we were getting too much head loss. Let's do something that will cause us large head loss. Let's go back to the velocity to keep it simple. Let me show you 5 feet per second again. You know, all of this is tied together down to this final number. So it's going to require 2.6 kilowatts to pump fluid through this pipe at 5 feet per second. Let's go to 10 feet per second. Let's double the velocity. So instead of 225 gallons, it'd be like 450 gallons. Look, it was 2 something, now we're at 10. We increased the electrical power or the horsepower required by almost a factor of 4 by doubling the velocity. So remember this, 14 horsepower. Let's suppose we can't live with this size pump. Let's select a larger pipe. Let's go to 6 inches. And let's go back to GPMs because I know that 10 was, I don't actually remember what 10 was. It was about 450 gallons. So let's put 450 gallons here for the next size up, which drops the flow in a 6-inch pipe to 4.5 feet per second. Okay, and look, we've dropped the horsepower requirements, cut it in half, as well as the power required to pump this 450 gallons approximately. So you can use it to do what-if scenarios on different diameters at the click of a button, essentially. All the physical properties that you need to do the analysis is in the database for all of the products. I haven't shown you all the products, but there are a lot of CNI products registered right here. The Bondstrand series, the Centricast series, the Green and Red Thread series, and Silver Street. Pretty much sums up the flow analysis. And let's just key on that. Remember, I was running 10 feet per second. I had a huge pump requirement. So I upsized my product, same flow rate essentially, and lowered my velocity. Now, yeah, it dropped these numbers here, but there's another reason for that, to keep your velocities down in the sweet spot. There's a reason to avoid 10 feet per second unless it's absolutely necessary, or even greater velocities, 15 feet per second, 20 feet per second. So it all comes together under the WaterHammer module. Okay, here it's loading. See, the last time I was looking at the other module, you can actually have both these up on two screens if you'd like and split your screen. I was looking at 4-inch. Let's see what the input is here. Here's the input. You need to give the software your operating pressure. Let's say the pump is putting out a pressure of 100 psi. You need the pipe elastic hoop modulus, which is going to pull from the materials database. It's done that for you. Then you need to know properties of the fluid. This was water in this case at ambient temperature, and it so happens we have the default values for the fluid bulk modulus and density and specific gravity already as defaults. If you're going to run sulfuric acid, these numbers would be drastically different, of course. And the default start here is also 5 feet per second. So I could put in 4 point something, but let's just leave it at 5 and see what we've got. So at 5 feet per second through a 4-inch pipe, you're seeing 100 and potentially 122 psi WaterHammer or surge pressure. And the surge pressure will be additive to your operating pressure of 100 up here. So you can see how we get the maximum pressure in that piping system to be 222 psi. Okay, and this is essentially due to a surge pressure running through the pipe at a wave velocity of about 800 feet per second. It happens very fast. I believe we were looking at, what, a 1,000-foot line. It could go down to one end of that, bounce off the end, and bounce back in less 1,800 feet per second. It takes less than 2 seconds to travel to and back to the beginning of that pipe, assuming it started at the beginning of the pipeline near the pump or valve. Okay. Let's look what happens if we wanted to run 10 feet per second through that. Actually, I'm going to go ahead and change diameters because I now remember I was looking at going to a larger diameter to get the velocity down to around 5 feet per second. Look, the diameter change didn't make a lot of difference on the surge. And why is that? Because the elastic properties are the same, and as long as the pipe diameter to thickness ratio, you know, how big the pipe is compared to the diameter, if they're virtually the same ratio, the surge pressure is going to virtually be the same number. Well, it would be exactly if the pipe were same exact ratios. So we're still looking at 119 psi, 219, and you could run this to the piping system, no problem whatsoever. Let's go back to the 4. I should have started with 10 foot per second here to startle you. Okay, 5 gave me the 122 surge. 10, I'm typing this in from my keypad, essentially doubled it to 244 psi surge. Our operating is 100. Our surge is 244. You combine them, you're looking at 344 psi. I believe I recall that 4-inch green thread pipe was rated, I believe this was a 300 psi number. If so, you should have a little concern here because you're actually overshooting the pressure rating of the pipe itself. So So this is another reason to avoid high velocities. 10 is not what I would call a sweet spot. Remember I was telling you anywhere from 3 feet per second, 73 psi surge. And these surge are worst cases. They're assuming, the calculations are assuming a worst case event, such as an instantaneously shutting off pump or valve. Things don't really stop instantaneously. There's a few microseconds that'll go by. And those few microseconds can make a big difference. If you had a delay, if your pump started up or stopped slowly, or if your valves closed slowly, say over a period of 10 seconds, 73 wouldn't exist. It might only be 10 psi. That type of analysis is really going to require, if you're going to get to that kind of detail, it's going to require the engineers, the end users, to run some type of dynamic system analysis. Because if you're going to try to get that close, then you need to account for every item in the piping system, not just a pipe. You've got to consider valves, restrictions, tanks, pumps, everything. But you can see by dropping it to 3 feet per second, the surge, the theoretical worst case surge, has dropped by about 30%, which is a good thing. 5 is 122, and 10 feet per second is 244. It looks linear. This is a function of the velocity squared. This will happen. If you had wanted, you could switch over to SI units, megapascals, kilograms per cubic meter, meters per second, etc. At the click of a button. By putting this unit switch here, it's cleaned the screen up tremendously. If you don't want to see some data, you can always close on these, but that doesn't make a lot of sense right here to close them. But you're going to see in the next screen how busy it is. That is a good function to recognize. So let's move on to, before I do any more engineering analysis, let's go to the chem resistance module. What the chemical resistance module does is it essentially replicates the printed chemical resistance guide that we have, which has over 750 chemical substances listed in it. We've incorporated them into our database for all the products. And here's some of the example chemicals in there. They're in alphabetical order. You can type in what you're looking for at the top, and it'll go straight to sulfuric, for instance. Or you can use what you see and just scroll down. So let's select glacial acetic acid. And what it has done for us, it's looked up all the temperature ratings for our product lines. You see Centricast RB, which is epoxy, Centricast CL, which is vinyl ester, Z-Core, and you can go through all these and see all of our products. What's important here is you're looking for a maximum temperature rating in this glacial acetic acid for these product lines. I'm seeing 75 degrees on all of these. Here's one that's not tested. Over here, I'm seeing this is a CL vinyl ester series. It's not recommended. Another one down here is not recommended. These two have something in common. They're both vinyl ester. So it sort of guides you as the user as to whether you need an epoxy system or a vinyl ester system. Now, bear in mind that sometimes vinyl ester and epoxy work as well as the other in water, salt water, for instance. But I did pick glacial acetic acid knowing there was a distinction. If you see not recommended highlighted in pink, avoid that product. You do not want to put it there. You will have corrosion or chemical attack issues, undoubtedly. Do not put any of these products right here, RB1520 or 2530, in this service if it's going to be operating continuously over 75 degrees. Okay, so this is a guide. Let's look at another one while we're here. Let's look at beer. See, it looks like every pipe we manufacture is capable of transmitting beer through it. 200 degrees max temperature for vinyl esters, 200 degrees max temperature for the RB epoxies. Z-Core, 250 degrees. That seems like it would run your beer. But anyway, this is how you use the chemical resistance guide. And again, it's very, very quick itself. So chlorine dioxide, less than 15%. You see some here that are not tested. And a lot of people say, why have they not been tested? It's really got to do more with the historical approaches of the companies that have become fiberglass system. This down here was, you see the product was Bondstrand 5000 or 5000M. This was, Bondstrand was a trademark product for Amaron. They never tested it, probably had no request for chlorine dioxide. Why? Because they had the Bondstrand 2000 series up here in 4000 that worked just fine, and this is what they traditionally sold. It wasn't necessary to be tested. So it doesn't necessarily mean that they will not handle the service, it just means simply what it says, not tested. And again, you've got your upper limits. If you had an application where it was running as high as, say, 175 degrees, it would eliminate all of these because none of them are as high as 150, except for this one down here, and it's our custom filament wound line vinyl ester piping, better known as FChem. Okay, let's switch. I think that's enough on the chem resistance guide. Let's go to the span and thermal analysis module. Let's just stick with the green thread 4-inch we've come up with. Everything here on the left side is input. We also have more input on the right side of the screen. Very busy module. For now, I'm going to close some of this to guide your eyes to the span analysis part. Let's set the pipeline loads. Well, what are we talking about? We're talking about span, maximum continuous spans. Well, to calculate them, you have to know what's inside the pipe. So in this case, we handle it by the specific gravity, which in essence gives us the weight of the fluid. So we'll set it at 1.0 as a default, which is water. If there's external loads on this pipe, what do you mean external loads, Mike? I mean if there's insulation on it, there could be as much as possibly a half a pound per foot of external insulation, for heat, to prevent heat loss. If it's in the north, it may have a large buildup of snow on the top of it, or possibly ice on top of the insulation. So you can always account for this external load, and you can say 2.2 pounds per foot. That accounts for the ice and insulation. What kind of input do you need? For the thermal analysis and also to calculate the spans, you've got to have the operating temperature. The default is ambient or 75, and the default installation is ambient, 75. Well, let's look at what happens if our operating is at ambient. What are our supports? Or our support links or spans? 16.61 feet. What if we're operating at a higher temperature? Say 145 degrees Fahrenheit. Program goes out, gets the material properties, the modulus, as we talked about earlier, at 145 degrees. It comes back and it says, now your maximum continuous span is 15.15 feet. By increasing the temperature, we actually reduce the recommended span. Now, what do we really recommend when we recommend these spans? We're recommending a pipe that will not deflect more than 1/2 inch. That's the default value. 1/2 inch deflection is a very good number for most piping systems. It's been used for 60 years. Remember, 60 years ago, at Smith, they only made 2-inch through 16-inch pipe. 1/2 inch deflection looked good for those size pipes. But you might think that if you were doing a 1-inch diameter pipe, 1/2 inch deflection may look like half the diameter and may appear a little poor to the eye. It may not drain well either if you tried to drain the system down. It was deflecting a 1/2 inch. Or what if this were a 42-inch diameter pipe? This pipe does go to 42 inches. 1/2 inch criteria may be a little bit too stringent because when you unload it off the truck, you probably got a 1/2 inch deflection. It's probably pre-bent that much to start with. So to give you a little flexibility, we have incorporated this mid-span deflection. The default is a 1/2. If you wanted to change it to be more stringent down to 0.28 inches or increase it, well, I'll let you increase it up to 1 inch. I'm not going to let you get crazy here. But you can change your span deflection. And it'll recalculate the numbers. 0.43 is reflected here in the output. And the continuous span length actually changed a little bit for us. As you put in a lower span deflection, you get a shorter span that you may use to maintain that deflection. Now, that's not the only criteria the software uses. It also uses the bending stress due to all these weights of the pipe and the external loads and the fluid inside. It calculates the bending stress. Now, it does look at this bending stress and compare it to that design envelope that we saw much earlier, the 20-year LCO design envelope. And it ensures that we stay inside the safe zone, inside the trapezoidal design envelope. It even takes into consideration the internal pressure. Suppose you're operating at 158 psi. It calculates the stresses due to internal pressure. If you see no change here, then we're still inside the envelope. If you go too high, let's remember this. Let's get this back up to a little more deflection here. It'll make it more obvious. See, I cranked this up to allow 0.68 inches of deflection. I have 158 psi internal pressure. But when the calculations were performed, it says you may allow 0.68 inch deflection, but if you want to maintain your stresses inside the design envelope, you can't have a span greater than 15.26 feet, and the mid-span deflection, if you're curious, is 0.52 inches, and here's your bending stress. So by including the internal pressure, you will stay inside of the design envelope. For internal pressure, all the external loads and dead weight on the pipe. Now, don't think this is the last word in piping design, because there are other stresses, but these are the main ones. Let's look at the thermal gradient. I see my 45 minutes. I'm coming up on it really rapidly. But if you look at our thermal gradient, it's 70 degrees here. My operating is 145. My install is 175. The difference between those two is 70 degrees Fahrenheit. What are we looking for here? We're looking for the thermal expansion of this pipeline. Now, the base over here was 100 feet in length. So it says every 100 feet of pipe will expand, if unrestrained, free to move that is, 1.16 inches for this thermal gradient of 70 degrees. Now, if you wanted to have a longer line, like 956 feet, you don't have to do ratios. I'll calculate that for you too. 11.08 inches of thermal expansion. That's quite a bit of growth. Okay, let's look at the pressure considerations here as well. Remember, we were setting this up for 158 psi internal pressure. The pressure expansion due to that will be 4.8 inches and change over this 956-foot run. It's actually broken into two parts if you want to look at the deep engineering on it. You have your Poisson's effect, which actually tries to shrink the pipe when you pressurize it, and then you have your axial thrust growth due to the pressure on the ends of the pipes, the fittings and changes in direction, which is 16 inches. So the combination or summation of these two gives you the 4.8 inches right here. And just to sort of echo and make it easy for you, recall that the thermal expansion was 11 inches up here. You can sum this up with the 4.8 for the pressure expansion, and you see that the total is thermal plus pressure is almost 16 inches. Okay, I'm going to stop right now and allow questions because we're at the 10:45 mark, and as you can see, we've gone through everything except for the buried pipe energy loss module. It's relatively straightforward. Functions very much the same. And if you need help with it, you can please give me a call. I'll be happy to discuss it with you.
If you do have any questions, there is a chat box. Just please type in your questions, and I will read them off to Mike and get some further answers. Okay, we don't have any questions yet, Mike. I mean, if there's some other things that you want to demonstrate for the remainder of the time, feel free.
I would. I want to go right back to the span and thermal analysis module, okay? I want to really go back to the spans, the maximum continuous spans of 15.2 feet here, for instance. What is a maximum continuous span? I'm often asked. Let's look at an example right here. Let's look at a piping support model, which we'll look at the supported elbow model. It's a pictorial. If you've seen our printed catalogs, you've seen this exact same model, the same factors and things are used in it. So this is a replication of the product data sheets at any temperature and diameter at the click of a button, I must say. But the nomenclature here, L sub C, stands for continuous spans, okay, or continuous support spans, as the software says. And if you had an anchor here or a fixed rigid point, and you go along, these are all treated as continuous spans. But when you get to an elbow, I'm going to slide this up a bit. Let's suppose you've supported that elbow. It's kind of hard to do in the real life. You might support right over here next to it, either side. It doesn't really make much difference. But you're supporting that elbow so it doesn't deflect. What you need to do to maintain your, suppose our criteria was a certain bending stress and a certain deflection, which we know it is. To maintain those stresses, and stress is the most important component here, you need to shorten this A to stay inside the design envelope. And let's look at the comparison between LC and A. LC is 15.3 feet and 3 feet. A needs to be reduced from 15 down to about 12 feet. So these links right here need to be about 3 feet shorter than your continuous spans. If sometimes you grab a number, you say, my span is 15 feet, and you make everything 15 feet, and you go out in the real world after it's installed and been in service, you'll see maybe a little more deflection here than you anticipated. Mainly because when you go around the elbow, this pipe here, when it sees this elbow, this pipe in torsion is not nearly as stiff as this pipe here is bending, so that allows it to twist more here, and you get a larger deflection. Okay. Control deflection, control stresses by incorporating this reduced length. Let's go to the other model.
Mike, I do have a question.
Sure.
Somebody says, will FChem ever be included in this program?
If we ever develop a FChem pressure class and have published literature, that answer is absolutely yes. Right now, I don't have a guide, essentially a database to put in here on FChem because it's all custom. It's very doable, though. I guess I could build you guys a module where you could design your own pipe and then start with what you guys come up with. Be kind of cool. Let's look at the unsupported elbow right here. Very similar to the one before, except an unsupported elbow is not supported. I like to call this a dangling elbow. I also like to say this is not something I want to recommend because these dangling elbows like this have a tendency to vibrate up and down. They just don't stay steady under most flow. I've experienced this in a couple of jobs, and it's not something you want to see. But there's cases where you cannot get close to this elbow. It can happen. Or the designers don't want to design the extra structure to get up in there. That was a case I've seen in the past. So if so, and you want to keep your deflections and stresses in check, then A, B, C cannot exceed these values here. It's the same example. The continuous span is 15.3 feet. A plus B, the sum of the two, can't be more than 11 feet and a half. And then these C values can't exceed 12 feet, same numbers before, I believe. And then we got an odd number here on the end. Suppose you were running SRAM core down to a tailings pond, and all you did was leave the pipe open. Actually, if you want to keep the deflections and stresses nice and cooperative down here, you need to reduce these as well. So look at D. It really gets chopped down from 15 to 10 feet. So you lose 5 feet here. So if you want it to be pleasing to the eye and you want to keep your stresses low, reduce these links. I've rarely or if ever seen that. Usually when you're that close to the pond, it seems like it's an afterthought. Let's go back to the software if I can figure out which one it is. Here we go. And we have one more model here for you. And I didn't really discuss this in detail. I skipped through it. I shouldn't have. It's for an expansion loop. Suppose you had thermal expansion and pressure expansion, which we discussed earlier. If I can find the button. It's going to take me a minute. Remember, we had our unrestrained thermal expansion of 11 inches, and then we had additional expansion due to our pressure of almost 16 inches. Let's look at the thermal component of that. The pressure is a little bit tricky, so it only does the expansion loop calculations for thermal, and there's reasons for that. It gets to be a complicated engineering design. But here's what we're talking about. The LC is our continuous spans. You're coming up to an expansion loop. Well, it's a change in direction, and it's supported near it. It should be always supported near it. So you've got to reduce this length to A, which is the same A as before, or 12.21. Now our offset, this is what we're trying to do, come up with how much of an offset we need to make this thing absorb the deflection. And that is L, which was right at 27 feet. It's a pretty good offset leg. I chose a pretty high criteria for this. So that is your other model. And other ways of controlling thermal expansion is by using expansion joints themselves. And if you're going to use an expansion joint, you need to know the capability to compress to move that expansion joint so it'll function. Well, what is the pipe capable of, you might ask to start with? A 4-inch green thread pipe with all this input, if you try to restrain it, keep it from moving, it'll create up to 544 pounds of load. So 544 is your maximum load that you can use to compress an expansion joint. But you cannot do that, because as soon as it has to be much larger, this value has to be much larger than essentially the spring rate, the amount of load it takes for pounds per inch deflection to deflect that thing. I say a good starting point is to take this number and divide by 4. Let's just say it's 125 pounds. You need to use an expansion joint that requires less than 25% of this to actually close it or open it. So this is a good rule of thumb. And I would actually go to the vendor and look at the specs for the expansion joint itself, because it could be that you can get one instead of 125 pounds, that you might get one to activate at, say, 50 or 60 pounds. I would choose it, especially if it's got the ability to absorb, this is a lot, 11 inches. Okay. Now, at the end of a long run where you put an expansion joint in it, somewhere you're going to have to overcome this internal pressure load, because it's a big thrust, like on a fire hose, if you can imagine that hitting you. And the total load to restrain, I should say, and this will be like an anchor at the end. It's what we call anchors. They restrain axial movement. It's not going to be the 544 pounds down there. That's just the load it takes to restrain the thermal growth. It's this pressure load right here, 3,000 pounds. Your anchors at the end of your runs will have to resist 3,000 pounds. It seems like a lot of load, right, for a 4-inch pipe, but it's mostly due to your pressure. Okay, it's about 5 till. Any more questions? Okay, I'm going to go on to one more. I can't leave the buried pipe energy loss module on like that. Same type of input. Let's go to something you and I are now familiar with, green thread HP. Let's go to the 4-inch pipe. Most of this page is input. Okay, it's settled down. Notice my pipe length, the minimum pipe length is 880 feet.
There is a question, Mike.
Okay.
Why do you need an expansion joint on green thread?
Well, you don't need them necessarily. I'm going to go back to the span module. And I'm going to reset these parameters. But if you have an expansion of a piping system, green thread, red thread, bond strand, it makes really no difference. If you have 10 inches of growth, I believe that's about what we had a while ago, 10 or 11 inches of growth, there are several ways to, I'm just going to pick a temperature here. I'm going to pick a length, 1,000 feet. We have an unrestrained thermal expansion of 9.4 inches. Okay, we can control that several ways. We control it with an expansion loop leg, the 17-foot leg. That was the L value we saw in our little model. Or we can control it with a change in direction. I don't have a model of this, but it's in our engineering design guide. It has to be 25 foot. Or we can restrain that growth, put anchors at the end of the line and restrain it. And if we do, the thermal restraint will be 449 pounds on those anchors at the end, but then you must guide the pipe. And you've got to put a guide every 28 feet And what's a guide? I think of it as a U-boat as a simple example. So every 28 feet it would have to be guided if you restrained it, anchored the system. And remember, we've already got supports every 16.76 feet. I would just say guide it at some value less than this, and I would do it at every support. So I would guide it at every 16.7 feet, for instance. Okay. Now, if you anchor that, those anchors have to restrain the thermal load, 449 pounds. If you're operating at some kind of pressure, say 142 psi, it has to restrain that value, 449, plus the pressure thrust load, which we've summed up here as 2,700 pounds. What we're looking at, 4-inch pipe. So anchoring, you have to worry about the anchor loads, and you have to guide it. If you can't do that, suppose you're in a above grade system hanging from hangers, hanging from a roof. You've got rods hanging down on this fort, holding this pipe up. There's really no way to restrain a pipe with hanging rods. You've got to build structure up there. It takes a lot of structure to restrain 2,700 pounds in a ceiling that's 30 foot off the ground, for instance. So therefore, it might be more efficient for you to put expansion joints in the ceiling, and you don't have to deal with as much load. Quite frankly, flexibility is the way to go. I've almost forgotten if the question is if we do use it or don't use it. You actually have a choice. You can use flexibility as an expansion loop, changes in direction. You can anchor the system and guide space it, or you can install expansion joints themselves, commercial expansion joints. So there's no one best solution. It depends on the system. That's mostly left up to the design guys up front. I would hope these design guys are encouraged to use this software to look at these different variables right here that you brought up. Because the whole purpose of Success by Design is not to do a super detailed analysis for the engineers. It's really targeted at the preliminary design guys. You don't have to be a stress analyst to use this program and do a baseline design of the piping system, support spans that changes in direction, prediction of how much the pipe's going to grow. If you can tell if a long run's going to bang into a pipe adjacent to it, for instance, the designer can avoid that way before it's finalized and goes to the stress analyst. The guy who does flexibility analysis is usually way downstream, maybe months, maybe years. So this is really, I think, a preliminary design tool. Sort of.
Hey, Mike, can you show where everybody can go to start using software again?
Yes, I believe. Okay, if you can. The link on the web is right here, https://cap.nov.com. Now I'm going to click on that. It takes you right here to the CAPS Connect page. If you've already registered, all you do is hit log in. I'm already logged in, so it wouldn't work too well. If you're a first-time user, click here, read the document carefully. Probably it's more difficult to register than it is to use the software, in my opinion, because IT guys always have their quirks, and you must do it their way. So read the instructions, then come back here and do My NOV registration. When you go there, it's relatively straightforward. You type in your email address, your first name, your last name. Notice there's a lot of fields here. They're not required. But we would like to know who you are. We've got to have your email address. That's mandatory. We'd like to know, and we'd like to know who you represent company-wise. And you also must create a password. And you're responsible for keeping this password, although like most places, if you forget it, you can when you try to sign on, say, I've forgotten it, and set up a new one. And then you submit your registration right here, but not after you've read these terms and said, I've read the terms, I accept them, now I want to register. I'm not going to click the button because it'll give me errors because everything's blank.
All right, thank you, Mike. I appreciate it. And I do appreciate everybody joining on the webinar. As I mentioned earlier, we have recorded this webinar, and we will be placing it on our website, which you can go to, which I believe is nov.com/FGS webinar to view this in the future, or you can send the link to somebody else for viewing at a later time. And thank you, everybody. I appreciate you joining us, and have a wonderful day. Thank you.
Thank you, Lance.